All right, my little babies. Nice to see you guys again. Time to get going. We're going to be talking about volume today. We're going to learn what volume is, how it works with different situations. Some questions are harder than others. We're going to move at a pretty quick pace. You can always pause the video, rewind all those things if you need to. But essentially, like, what is volume? So imagine like this is like some sort of pentagon-shaped cheese block. And every time you cut the cheese, right, you cut a shape off. Each one of those slices of cheese would be pentagons, right? Wouldn't each slice of cheese look like that? And you slice and you slice and you slice and you slice. And you could just keep cutting the cheese, keep cutting the cheese, keep cutting the cheese, right? Well, how many would there be? Well, technically, it's kind of like infinite. But what volume is doing is basically getting the area of one of them and multiplying it by how many it takes to fill in the space. And there you have volume. Volume is the amount of space an object takes up. So it is the area of the base times the height. Let's do some problems involving volume. So here's a regular triangular prism that has a height of 7. The height of the prism is 7. That is the edge that connects the two bases. They tell you that the base edges are 22. So one thing I've really stressed since like January is that you can find the area of an equilateral triangle. If you can find the parts of an equilateral triangle quickly and correctly, I need the area of this triangle. So what do you have to do? You have to drop it like it's height. That would cut this side in half. It becomes a 30, 60, 90. So this would be 11 root 3. Knowing that pattern and doing it quickly can make this so much less painful. People that can't do that quickly and correctly, what should be an easy problem becomes a very painful problem. So we drop the height, cuts the side in half, 30, 60, 90. So this would be 1/2 times the base times the height. And that would be 121 root 3. So that's the area of the base. And then the height is 7. So it's 121 root 3 times 7, which would be 700, 147, which would be 847 root 3. And that would be this triangular prism. Then we talk about cylinders. Guys, this is the same formula. This is still capital BH. It's just because it's a cylinder, this is the area of the base. Pi r squared is the area of a circle. The base must be a circle. So a lot of times, if it's a prism, the base can be anything. It could be a triangle. It could be a pentagon. It could be, whatever. It could be a calculator. It could be any shape. I don't know. That's a weird example. But the base could be any shape. But for a cylinder, it's got to be a circle. So they go ahead and plug the circle formula in there. So let's do a cylinder situation. Here we have a cylinder with a cylinder removed. For volume, because it's just the space it takes up, we don't care about individual surfaces. This is not surface area anymore. This is volume. So we can do the volume of the big cylinder and subtract the volume of the small cylinder, and we're done. Well, that's going to be pi times r squared times h for the big cylinder minus pi times r squared times h for the small cylinder. This would be 1,500 pi, and that would be 25 times 15. That's going to be 375 pi, and then the answer would be 1125 pi. They do tell you to round to the nearest tenth on this one, so 1125 pi. Type it in. That would equal 3534.3. Make sure you round the way they tell you to. Here's another situation, has a cylinder and a prism. It's a rectangular prism. One thing I want you to note, like if you have a rectangular prism, it doesn't matter which face you call the base. And for volume, like if this was like 10 and 12 and 6, like if you call the bottom the base, you're going to do 10 times 12 and then times 6, right? You do 10 times 12 times 6. Well, what if you called the front the base? Well, now you're going to do 10 times 6 and then times 12. But does it actually matter what order you multiply in? No. So for rectangular prisms specifically, you can just you just multiply the three numbers. The area of the base is the length times the width times the height. And it doesn't matter which one's which. It really doesn't. So in this problem, if I'm looking at this, we have a 6, a 14, and then front to back we have a 12, right? They tell us down here it's 12. So front to back is 12. So this is just 12 times 6 times 14. That's going to be 72 times 14. That would be 720. That would be 280, and that would be 8. So that would be 1,008. So that's the box part, length times width times height. Then we look at the cylinder part. The cylinder part is pi times the radius squared times the height. So that part is 64 pi. And the final answer will be the cylinder plus the box. And we're done. It's not surface area, it's volume. It's just how much space does it take up. How about pyramids? Okay, pay attention to this. Don't fast forward. You need to understand this. This is 1/3 BH. That means how many pyramids could fit into a prism that has the same base and height. So like if I were, let me trace this base real quick. So if this base looks something like this, if I had a prism with the same base and the same height, I know what you're thinking. You wish you could draw this good. So there's my box, right? Let's say that they have the same height. They have the same base. How many pyramids could fit in the prism? And the answer is 3 of them. If they have the same base and the same height, you could fit 3 pyramids into the prism. That's because the pyramid is 1/3 the area of the base times the height. So if these two numbers are the same, then the pyramid is 1/3 the size. Now, this is kind of a tricky situation. A lot of people can't wrap their heads around this because they try to fit the pyramid into the prism. If you actually take the pyramid and put it into the prism, it's not a perfect fit, guys. Oh, I didn't make this height the same, but it's not a perfect fit. I don't know if am I making it worse? It's close. But there's no room for more pyramids. There's no room for it. But if you were to like melt it down, like what if you melted down the pyramid? Would they all fit in there now? Yes. But physically, as they sit, you cannot fit 3 pyramids into the prism. You can't do it. You can fit 1, but not the other 2. But we're talking about just how much space it takes up, not the current shape. So we can change shape. We can melt it down. Or one way I like to think about it is, what if these were cups? How many pyramid-shaped cups could you pour into a prism? The answer is 3. The answer is 3. What would you? And here's a follow-up question: what would you have to do to the height to make them have the same volume? Well, if you made the height 3 times as much, now they're the same volume. So if the pyramid is 3 times as tall as the prism, but they have the same base, they're going to be the same, right? Because what is 1/3 times the same base times 3 times the height? Well, the 1/3 and 3 cancel out, and now that's just the same volume as the original prism. All right, I hope some of that made sense to you. Let's do some problems. Before we do this, we need to understand there's 2 situations. I might give you the lateral edge, which is this piece. I might give you the slant height. Those are the 2 things I might give you. Your goal is to get the height, and that's this number. So you need to picture 2 things. The first thing is the lateral edge and the height are connected by this number. That is called the radius. So the blue triangle here is a lateral edge, the height, and the radius of the base. The other situation is I give you the slant height, and you have to use the apothem. So the pink situation is the slant height, and the apothem get you the height. And I know I've showed you this stuff before, but if we look at my little pyramid here, where is all this happening? Well, right here. Here's my lateral edge. It starts at the apex and goes to the corner. What connects the lateral edge to this thing inside? That's the height. The height is on the inside of the shape here. What connects them? It's this diagonal line. This is the radius, right? That's this line down here that connects the corner to the height. So we need to be able to recognize that right triangle. The other big one is the slant height. Here's the slant height. Maybe looking at it from this side, what connects the slant height to the height? Well, that's this line. Flip it over, that's this, right? What connects the middle of the side to the height? That's the apothem. So you need to know which one you're working with. You're going to have one of those two situations. You're going to either use the apothem or the radius. For this particular problem, they gave us the lateral edge of 30 and the base edges are 10. So if I draw the square, 10 and 10, the entire diagonal would be 10 root 2, right? I didn't actually tell us, sorry, square base. I should have put that in there. So that means that the part we care about for our triangle is 5 root 2. On a square, it's going to be half the size. The radius is half the size, right? The radius would be just this much. So we have a right triangle that we're going to work with that is 30 on the hypotenuse and 5 root 2. Practice doing this without a calculator. I'm going to do it right now, but you can pause and practice. But we reduce by a factor of 5. 30 divided by 5 is 6. 5 root 2 divided by 5 is root 2. We do Pythagorean theorem on those numbers, and we get 36 minus 2. So that is the square root of 34. We multiply the 5 back in, and we get our height. So at the end of the day, this is 1/3 times the area of the base, which is 10 times 10. 1/3 times the area of the base times the height. And nothing here is divisible by 3, so that's going to be 500 root 34 all over 3, bada bing. So pyramid questions really get people. One of the things I'll point out real quick, how do you know if a number is divisible by 3? So like if I said 1671, is that divisible by 3? How would you know? Add the digits, 1 plus 6 plus 7 plus 1. That is 7 plus 7 is 14 plus 1. Those digits add up to 15. Is 15 divisible by 3? Yes. That means this is divisible by 3. If the digits add up to a number divisible by 3, then the actual number is divisible by 3. And that way you can know, let's see here. Boom. So it's 557. That's pretty cool. Okay. Cone is the same idea, but there's only one right triangle to worry about. It's this one. It's the radius, the height, and the slant height. It's the only one we care about. So if I give you the slant height, you get the height using Pythagorean theorem. All right, the circumference is 22 pi. Circumference equals 2 pi r. So 22 pi equals 2 pi r. Divide off 2 pi, and r is 11. You should be able to go from this to this pretty much instantly. This number is the diameter. You can also write circumference as pi times d. This is the diameter. Therefore, 11 has to be your radius. I want you to get really good at that. So in this picture, we need the height. We have the radius. We have the slant height is 66. I want you to pause the video and do Pythagorean theorem on 11 and 66. No calculator. But it would be 6 and 1. So that's the square root of 36 minus 1. So it's the square root of 35. Multiply the 11 back in. That's 11 root 35. Let's go a little bit thinner. That's 11 root 35. Okay. So our actual problem is going to be 1/3 pi times the radius squared times the height, 11 root 35. So this would be 121 times 11 root 35 divided by 3. 121 times 11. Here's a little trick. You don't have to really know this, but this is pretty cool. Because you're multiplying by 1 a bunch of times, there's an easy way to multiply by 11. So sidebar, you don't have to know this, but sidebar, we take the last number 1. Look at the number 121. We know that 1 times 1 is going to be 1. The next number in is going to be 2 plus 1. If you multiply them both by 1 and add them together, you're going to get 3. The next number in is going to be 2 plus 1 again, and then the first number, 1 times 1, is going to be 1. So 11 times 121 is 1331. There's a root 35 on it, divided by 3. Is it divisible by 3? 3 plus 3 plus 1 plus 1 is not divisible by 3, so we know that we are done. Pretty cool. We're crushing it, guys. Sphere formula, know it, love it. Real quick, though, what if you were doing 60 times, actually, let's change it. Let's do 66 times 4/3. So you're going to have to multiply things by 4/3. How do you multiply by 4/3? Well, if I said, hey, what's 66 times 4? Oh, too long. You don't know it. You had to think real hard. Takes a long time. But what if I said, what's 66 divided by 3? Ah, that's 22. What's 22 times 4? Ah, that's 88. See how fast that was? Always go small first. You guys that go big and make these big numbers and then can't divide them, no. Divide first. We've talked about this since September. You reduce when possible first. It makes it less work. So you're going to be multiplying by 4/3 a lot of times. I need you good at multiplying by 4/3. What is the largest possible? The largest possible circle has an area of 400 pi. Well, area is pi r squared. So 400 pi equals pi r squared. Pi's cancel out. So 400 equals r squared. So the radius must be 20. So this is 20. We know that it's 4/3 pi times 20 cubed. So that'd be 4/3 pi times 8,000. Is anything here reduced? Can you divide anything by 3? We always try to reduce first, and we can't. So this one, we don't have to do that. So we're going to multiply. We're going to get 32,000 pi over 3. Just so you know, 32,000 over 3 pi, those are the same thing. They're the same number. Don't get all caught up in that. Just don't put pi in the denominator. How many of the biggest possible circles are they? Just so you know, like the biggest possible circle could be drawn in lots of different directions. They drew the horizontal one, but it's the widest part of the sphere. All right, I want you to look at these two stacks of coins. Think about the volume, not surface area. The surface area is definitely going to be different, and we're not going to calculate that. Like these little sections, like you want to account for all those little pieces? No. Not talking about that. Talking about volume. What would you know about the volume of the two stacks? The answer is they're the same size. They're the same volume. So these are coins, right? Like they're the same number of coins. Even if I knock the pile over, wouldn't the volume of the coins individually still add up to the same number? Well, let's replace the word coin with cross-section. Isn't every cross-section a circle going all the way down? Isn't over here, it's the same circle. Now, it kind of waves. It does this like wavy shape, but the cross-section never changes. It's still a circle. Everywhere you slice, it's going to be a circle. So here's the thing. When you do a problem like this, it doesn't have to be perfectly vertical, but you do need that vertical number. The height is 12. So this, how do I know it's 12? I don't see it 12. It's 12. How do I know? Because this right triangle is a 3, 4, 5. 3, 4, 5 triangle. So I know that the height there is 12. So this is going to be pi times 4 squared times 12. That's the answer. That's going to be 16 times 12. That is 160 plus 32. It's going to be 192 pi. That's the volume of this cylinder. What's the thing that everyone does wrong? They use the 15. But what do we know about heights? Heights are the perpendicular distance. 15 is not the height here. 12 is. So you have that same height. Would these be the same height? Is each one the same? Yes, they're going to be the same height even though they're arranged differently. So be careful. Okay, how about water displacement? So I'm going to steal a little clip from someone on the internet here just so you can kind of watch this. But we got volume displacement here. Hopefully the ad is appropriate. I've had a few inappropriate ads, and it's a little scary. This is for Schwarz mirrors, trending in optics. I got a feeling that I don't need that. Bye, Schwarz. Okay. So, here we go. If we take this screw and drop it into this, I don't know what that's called, beaker, test tube, I don't know, cylinder, it's a cylinder shape. Notice that the water level rises. We don't have to calculate the volume of the screw directly. We can use the cylinder that the water makes. It's called water displacement. It rose, it was at 50, and now it's at like 57 or something like that. Could you get the volume of a person? Like here's the science teacher. Could we get the volume of the science teacher? Yeah, water displacement. See the water going out? Oh no. So as he goes into the water, what happens? It overflows. Why is it not letting me zoom in? I'm sorry, guys. And it's filling up this cylinder bucket that's on the side. And then it's easy to get the volume of that cylinder. It's called water displacement. His volume is going to match the volume of the water that leaves the tub. So we drop a rock into this shape. You notice that it has a height of 30 currently, and when it goes all the way up to a height of 35. Oh, that's really blurry. The only cylinder we care about is this cylinder. This cylinder is going to have the same volume as the object that was dropped into the water. And so it's much easier to get the volume of that cylinder. That's what we have to do. That's water displacement. So here it says, suppose a rectangular tank has that base. So let's draw a rectangular prism together. Not a tank that like shoots people. I'm talking about like a tank that has water in it. So I've got a rectangular tank. Its base is 5 by 12. It has water filled to a depth of 3. So right now, the water is 3 feet deep. I don't actually care about that. Don't care. What I do care is that when we put an object in, the water level is rising 2 feet. So I do care about this rectangular prism. So water is going to take the shape of the object it goes into. This right here, the black portion, is the part I care about. I don't care about the 3. I don't care about the 5. I care about the 2. I care about the area of the base times the height. That's what I care about. And that's going to be 120. So if it rose 2, it's still going to have the same shape. So the base is going to be 5 by 12 the whole time. You pour water in here, every one of these rectangular prisms is going to be a base of 5 by 12. Water takes the shape of the object it's in. So the water will be in the shape of a rectangular prism. It'll be a smaller one. The original water had a height of 3. Don't care. I do care that when I put an object in there, it rose 2 feet. That's the displaced height. That's the only height I care about. All right, let's do another one. Okay, so this is funky. Let's take a second here. I want you to focus on this corner, and I want you to make that the front. This is wacky. It messes with my head constantly. Does it look like these are stairs? Like this is a backdrop? Do you see the stairs? Pull that corner to the front. Focus hard. Do you see the stairs? Okay, now focus on this corner. What shape do you see? It looks like a sideways L. And then keep rotating, keep changing perspective. Go between corners. What do you see? You see stairs, L. Stairs, L. And it looks like it's doing this little jig. Yeah. All right, but we need to cut this thing up. It's a lot easier. Let's say that we slice it like this. Now we have 2 rectangular prisms, which are the easiest ones, just length times width times height. So for number 1 over here, it's 11 times 5. And then the height here is going to be 2 the whole time. So that's 55 times 2. That's 110. The second one is going to be, it's a little tougher. How long is just this part? Well, if this is 5, then what's left over would be 10, right? The entire top is 15. So that one's 10 times 4 times 2. And that would be 80. So we add those together, and our answer is 190. Break it into shapes that you can work with. And then one more question on here that we'll talk about. How many spheres could go into this shape? Now, again, don't get all hung up on could it physically fit. We're just talking about purely volume-wise. If you need to, just imagine like it's melting or something. I don't know. But how many would fit before it overflows? So I would love if you tried this on your own, but what's the first thing I need to know? I need to know how much space do I have. There's a cylinder shape of empty space. It's an empty cylinder that has a height of 4. So it's pi times the radius squared times 4. That's how much space we have. How much space does one sphere take up? Well, the radius is 3. So we would divide that by how much space they take up. 4/3 pi times 3 cubed. So this is the situation. It's the total. It's how much space we have divided by how much space each one takes up. Well, the top would be 36 times 4. That'd be 144 pi. The bottom, do this in your head. Right now. 3 times 3 times 3 is 27. What's 27 times 4/3? Hope you said 36. Right? 4/3 times 27. Divide first. You get 4 times 9. You get 36. And then we just did that. What's 36 times 4? It's 144. So what's 144 divided by 36? It's 4. So 4 would put it right at the top. No overflow. And that would be your answer. All right, I'm going to tell you one more thing. Bonus feature. What if it was 140 divided by 40? Just making something up. How many would fit? If one object had a volume of 40 and you had 140 of space, how many would fit? Well, 40 is 1, 80 is 2, 120 is 3, so we're at 120 when we do 3 of them, and then we're at 160, so this is 3 of them, this is 4 of them. Can we put the 4th one in there? The answer is no. So let me just real quick, what is 140 divided by 40? It's exactly 3.5. So rounding, a lot of people would round this to 4, but listen. If you put 4 of them in there, will it overflow? Yes. So the answer would be 3. 3, we're good. 4, it's overflowing. So you can't put 4. Can't do it. Can't do it. Even if it's like 3.99, can you put 4? No. The 4th one would still make it overflow. You got to be real careful with your rounding. All right, guys, that's an intro to volume. Hopefully you enjoyed that.